Hey physics students, Mr. Newton here. I just thought I'd go over a couple of these problems for this week to give you guys a little heads up on how to do it and how to be successful on it. And so let's get right to it. All right, here we go. Take a look down here at my old paper. And what we're going to be doing is looking at a new concept called oscillations. And oscillations are all about waves. So here's a wave. And waves have a couple of characteristics that you care about. Well, you should care about. You probably don't care. So first of all, they have a speed, meters per second. So we have a speed. They travel at a certain speed. Okay. And now all waves travel at all different sorts of speeds. You got light, which travels at like 3.0 times 10 to the 8th meters per second. That's fast. You got sound that's somewhere in the 340 meters per second range, and all different kinds of things. They all waves have their own speed, and then you also have wavelength. And so this is wavelength, right there, just the distance between the tops of the two waves, and then that is in meters. Okay, so meters. And then finally, we have this last concept where we have a thing called frequency. So imagine that I had this point right here, and I was measuring how many of these wave bumps pass this point in a given second. So you could call this waves per second. That's the frequency. Okay, so we call that frequency. So the frequency is how many waves pass a point in a given second. So you can imagine that if your speed goes up, your frequency will go up because more waves will pass a point in a second. If your wavelength gets smaller, your frequency will go up because more waves will pass there in a second. If your waves get bigger, frequency will go down. And the unit for frequency is 1 over s. Now, we just use 1 because it's not just waves, it's any cycle. So it's basically just one cycle. So 1 over seconds is kind of the idea. So just one, it's cycles per second. So that's kind of what we do here. And so it's a per second measurement. So if you look at that, we got our first equation, which basically says the speed, so the velocity, equals the wavelength, and wavelength we use that Greek letter lambda because just why not, times the frequency. All right, and so think about that. That should make sense. Meters per second equals meters times 1 over seconds. Ta-da! There it is. And so this is the only equation that you really need to know in order to solve the first set of problems. And so let's go ahead and look at a couple of those real quick. All right. What if I said that, one of the problems on there had a sound wave with a frequency. So we had a sound wave with a frequency of 197 hertz. 197 hertz. You might be like, what the heck is a hertz? Well, this is a hertz. The 1 over seconds is called hertz, named after, I think, the guy who made up that one, hertz, right there. So sound wave has a frequency of 197 hertz, and it goes, so let's say goes 91.4 meters in 0.27 seconds. Or 0.271 seconds, let's say that. So 0.271 seconds. So this is able to give us a velocity. So we got a distance over time. So there we get our velocity. So the question is, what is the wavelength? And then I think it also asks for the period, and so we'll talk about that in just a second when we get there. But first of all, let's solve for the wavelength, because now we have 2 out of 3 for this equation. So my velocity, so I got to solve for my velocity. My velocity equals distance over time, so that's going to equal my 91.4 divided by 0.271 seconds, and so I get a screaming 337 meters per second. Now, that's about right. Like I said, sound waves are about 340 meters per second. So there you go. They should all turn out about that through the air. But of course, when sound waves move through water, they go faster, and they go even faster when they move through solid surface. All right, so anyways, let's go ahead then and plug this in. So I got my velocity, I've got my frequency, so I can solve for wavelength. So I could say 337 equals my wavelength times my frequency of 197. It's about as easy as it gets right there. So my wavelength equals 0.762 meters. Now keep in mind that this equation always has to use meters in order for it to be true. If you got meters per second, meters and seconds, so you might have to convert prior to anything like that. The question asks you also for the period, and you might think, what the heck is a period? Well, a period is an amount of time, and so a period always refers to time, and it's time for a complete cycle, whatever that cycle would be. Now, in the case of this one, the cycle is one complete wave. So the period would be, if you were like tracking this point right here, the period would be the time for you to get back to the exact same point, right? So that would be a period. So a period, that would be one complete cycle, would be whoop, back to the same exact point. Or if you started here, it'd be getting back to that exact same point right there. But anyway, so a period is the time for one complete cycle. Now, how do you figure that out? Well, it's pretty easy. Period equals 1 over the frequency, and frequency equals 1 over the period. So this is about as easy as it gets, because you already know the frequency. So I could say, okay, well, the period is going to be 1 divided by 197, because I already know the frequency. It was that 197 number, so I'll go ahead and throw that in there. And that's going to equal what? Well, it's going to equal let's see, 0, sorry, I got to calculate this out, 0.00521 seconds. So there you go. And I think that problem asks you to change one of these, and you basically redo that all over again. Easy peasy. Here is some other ones. There's one on there that I think might throw you a little bit, so I'll just go ahead and do it. The idea was for an echo, so let's say you got a guy, woo, there he is, he's like yodel-ee-hoo, and he's like yodeling, and so then he hears it come back, woo, yodel-ee-hoo, comes back. All right, so let's say that the distance from here to here is, let's say 800 meters, and let's say he hears his yodel come back in, let's see, there's probably, 4.73 seconds. Let's go with that. Okay, so the question would be, what is the speed and what is the wavelength? Okay, so speed. We need distance over time. Now here's the thing, you gotta imagine about an echo. An echo, that sound wave is going to this surface and coming all the way back. So this distance is times 2 right here. So that's probably the only thing that this would throw you on right there. So 1600 is my distance divided by 4.77 seconds. Okay, so so let's say 77, yes, 4.77 seconds. So what is that going to equal? Like 337 meters per second. So hey, how about that? It ends up being about the speed of sound. What do you know? All right, so so that right there is one that might be tricky, but once again, it's the same exact stuff. And so on this one, they probably would also ask you what the wavelength is. So what does the wavelength equal? Well, that's pretty easy. You take our 337 equals my wavelength, and let's see. Frequency, see, they don't give you frequency. Well, they're going to have to give you frequency. So let's imagine that in the problem, they probably gave you frequency of like, I don't know, let's go 423 hertz. Okay, boom, boom. There you go. So go ahead and divide that out. And what's the wavelength? And so let's just say this is 423 hertz. So they'll give you that. So as you can see, this stuff is not super difficult at all. So 337 divided by 423, and so you've got 0.797 meters. So that's how big the wavelength is right there. You could also figure out the period by going 1 divided by the frequency if you needed to do that. Okay, so we have also got the idea of frequency and energy. So let me show you that, because they'll ask you, what happens when you are dealing with energy. And so what happens to energy? Well, here's like electromagnetic spectrum. So this is one type of wave. This is light waves, but this makes it easy to understand. So if you look at the different kind of light waves, here's radio waves. This is what we use for all of our, cell phone communication, everything. Microwaves, you can heat up food. Infrared, you can see in the dark. Here's light that makes us see in the day. Here's ultraviolet light that gives us a tan. Here's X-rays that shoot through our bodies and give you cancer. Here's gamma rays that make you have kids with 9 heads. So this over here obviously has higher energy. These are super high energy waves. And these ones over here are super low energy waves. They're not going to do much to you. So let's look at the correlation then. If you look at wavelength, 10 to the third is the wavelength. So that's a kilometer. So there's a kilometer in between the two tops of the waves on the biggest radio wave. If we look over here at the waves coming off of nuclear radiations, 10 to the negative 12th meters. And so it's little. So obviously as wavelength gets smaller, right, the smaller the wavelength, the more the energy, right? And so if you make a smaller wavelength, you have more energy. And that would correlate to frequency. So frequency is how many bumps pass a point in a second. Well, if a whole freaking lot of bumps, 10 to the 20th pass a wave in a second, that means that they're small. And so a lot of them pass. So the higher the frequency, the higher the energy. So you can see energy right down here is actually, we got this scale for energy down here at the bottom. So basically, as wavelength gets smaller, energy goes up, and as frequency gets bigger, energy goes up. So that's the correlation between energy and frequency. You got that. In the second set of problems you guys are going to be doing, it's dealing with springs. And so a spring is a spring does a little oscillation. So if I had like a spring, something hanging on the spring, like a little toy, little bobbing toy thing, it's like bloop, 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 hanging. I got a little doll that like bounces in my classroom to demonstrate this, but there's no bouncing in my classroom anymore. Sad face. All right, so anyways, this guy, he's bouncing up and down. And so you have a couple of different aspects going on here. You have the force, okay? So there's a force on this spring, okay? So I'm going to go force sub S, and that's going to equal what? It's going to equal the K, which is, this is the spring constant. Okay, so the spring constant is basically how stiff the spring is, and so it's going to be like newtons per meter, and so it's going to be the amount of force that it, well, I guess this is a big N, newtons per meter, the amount of force that it, and this is newtons, of course, because that's force, the amount of force per meter. So as you pull a spring further, right, the force goes up, right? So this is a spring constant. It's kind of like a slope on a graph, like if this is your distance, right, and then this is your force right here, your force is going to go up. The more you pull that spring, the tighter that spring gets, the higher your force is going to go up. So that's what that is. It's a a rise over run. It's just this slanted line right here, times what? Times x, and x is going to be your distance, okay? And distance stretched or compressed. Some springs compress. Distance stretched or compressed, and so that's what the x is going to be right there. Now, if I took this guy and I held him down here and just held it, I would have potential energy. And so we also have potential energy in a spring. So I could say, what is my potential energy of a spring? Or I could even write it like this. Potential energy of a spring is going to equal, it's kind of like kinetic energy, but you replace it with the spring stuff. So it's just 1/2 times the spring constant times the amount that you stretched it squared. So that's how you solve for potential energy of a spring. All right, so real quick, let's say we've got let's say on this spring right here, right up here, we've got a force of 56 newtons, and I stretch it a distance of, let's say, 18 centimeters. Okay, so let's say that I pull it 18 centimeters. So the question would be, what is the spring constant, right? So we just use this equation right here. So 56 equals K times my distance. Now remember, this distance has to be in meters right here. So if I look at this formula, right, it's going to be newtons equals newtons over meters times meters up here. So that cancels. So newtons equals newtons. And that makes that true. So that's got to be in meters. So I'm going to have to convert this to meters, 0.18 in order to solve. So my K equals 311 newtons per meter. Okay, so that's my spring constant on that. What about my potential energy? If I stretch this guy 18 centimeters, right? So I have 18 centimeters, I stretch this guy. What about my potential energy? So I could solve that. I'll solve that right over here. So my potential energy equals 1/2. I know that my spring constant is 111 because I just solved it up there, times 0.18 squared. Boom, boom, boom. And I get 5.0 joules. There you go. Easy peasy. So your two assignments, we'll just use those couple of concepts right there. So there's your equations for those. And that's all you're going to need. So you've got the velocity equals wavelength times frequency. You got the period equals 1 over the frequency. You've got the force of a spring equals kx. And you've got the potential energy of a spring equals 1/2 kx squared. All right, there you go, guys. Sorry that was so long, but I guess that's about how long it takes me to go through those things. Usually I don't like making videos over 10 minutes, but hey, you got to do what you got to do when you're on the coronavirus. All right, guys, miss you guys, miss seeing you, and hopefully this is helpful for you.